Okay, I guess we can start now. Okay, so welcome to this tutorial on adversarial learning for recommendation at this European conference on information retrieval. The tutorial will be presented by Walter Anelli, Yashar, Deldjoo, me, and Felice Merra. We are all from the same laboratory. We are from the Information Systems Laboratory at the Politecnico University, University of Bari. And in case you are interested in the topic, you might be you might find useful these two publications. The one published on the ACM computed surveys on the survey on adversarial recommender systems from attack defense strategies to generative adversarial networks. Or you could also be interested in the book chapter related to these topics in the upcoming third edition of the recommender systems handbook. As for the topic that we will cover in this tutorial, we are keeping updated this repository on GitHub, where we put all the approaches and algorithms which are published in the main conferences and in top journals. And well, of course, you can also contribute to add something if you cannot find something useful for you. And within this repository, you may find, of course, the paper, but it is very interesting to see that whenever possible, we also put the code related to the approach. So if there is the original code available, we have a link to the original code in case there is no code for coming together with the original paper, we try to implement it and make it available. All the implementation are also, most of the implementation are also available in this framework that we developed within our lab, this Elliott framework, which is a framework that is useful to set up the entire pipeline for your experiments with the recommender system. So with Elliott, you can select the models, and currently there are a lot of models already implemented within Elliott. You can select your splitting strategy. You can select the metrics with respect to which you want to evaluate your model, or with respect to which you want to train your model, and so on and so forth. So everything is covered. So you just have to to set up a configuration file and then just to run, and everything is done. And with respect to Elliott specifically, you can also find the implementation of algorithms for adversarial learning, as well as for generative adversarial networks, which are the main elements that we will cover during this tutorial for recommender systems. This is the plan for today. So in this initial start, I will just introduce some basic notions about, I will just give you a very few notions about recommender system, just 3-4 slides, no more. And then I will move to an introduction on adversarial machine learning. So all the problems, the different points of view, and the different goals of attack and defense strategies for adversarial learning. Then we will have the second part, which will be devoted to recommender systems and adversarial learning and generative adversarial networks. And then after the coffee break, we will have a practical hands-on session. In this practical hands-on session, we will play and we will work a bit with these algorithms and approaches, and we will also use Elliott for this. Okay, so let's start by introducing a bit the notions that will be used during this tutorial. So first of all, why adversarial learning is so important right now? Well, if we basically look at the trends on Google Trends about people looking for this adversarial learning stuff, so we see that starting from after the middle of 2016, this topic has grown in importance. So people are looking for this topic. So it is something worth studying and worth understanding. So because it is a topic which is quite hot right now. And also If we look at the suggested related topics, we see that if you search for adversarial learning, so Google also finds this related topics, which are, for example, generative adversarial networks, and this is one of the reasons why we will cover also this this specific topic in this tutorial. And also adversarial machine learning is suggested for you, generative model, and of course deep learning. And something similar, and you can also find in the related queries. And of course you can find a related query to deep learning, adversarial network, GAN, adversarial machine learning, and so on. So what is the focus of this tutorial? What is the main focus of this tutorial? Well, we will basically talk about adversarial learning for recommender systems security. And this is something which is at the intersection of machine learning, recommender system, and security. And we will talk a lot about this adversarial learning for security. But since the main idea that as we will see, since the main idea behind this adversarial learning for recommender system security are something that are also behind generative adversarial networks, then we will also talk about this this topic with of course with a specific emphasis on recommender systems. Adversarial recommender system for recommenders, adversarial learning, sorry, for recommender systems is something that is very popular in the literature right now. You know, in the last 3 years, more than 80 papers have been published in the main venues, in the main conferences, and in the top journals. So we also collected and discussed this these papers within our tutorial in case you are interested in you know, taking a look at the different approaches and a possible classification of all these approaches. But where are we now about this topic, and what is the contact point between recommender systems and adversarial learning? So as you can see on these slides, on the left-hand side, we focus on the evaluation goals of a recommender system, well, of a machine learning system, but with a specific emphasis on recommender systems. And then we see that we can have many evaluation goals. So we can have accuracy, a lot of beyond accuracy metrics. So for example, coverage, novelty, diversity, and so on and so forth. And on the right-hand side of the slide, you can see that we have different recommendation models. And these recommendation models have been classified in collaborative filtering, which are, you know, approaches that can be model-based, memory-based, or based on graph-based learning, and of course, based on deep learning. But we don't have to forget that we can also have content-based information that can be used to feed a recommender system, and this information can be, you know, whatever kind of metadata that you have. Can be text information that you have, or it can also be multimedia information, so images or videos or audio signals or music or whatever can be something that can be used together with the collaborative information to train your recommendation model. So this is where we are now. So we are interested in security as the evaluation goal. And related to the recommendation models, we will see that in this case, we are mainly focused on model-based, graph-based, and deep learning-based recommender systems. And the point is that we want to increase the ability of learning in adversarial settings. So this is the point. This is the point here. So all in all, the main goals of this tutorial are this one. So we want to bridge the gap between these two fields, so between the recommender systems and security. But in order to do that, we need to understand key elements and key concepts in adversarial machine learning. And this is something that we will do in the next, in a few slides. And then we are also going to better understand the differences that we have between adversarial machine learning and generative adversarial networks, and which, you know, they share this common term, which is adversarial, but we will see that they are used for different, for different purposes. What we really do want is that you must be able to code yourself and to write yourself the algorithms and to test these algorithms related to the, security and generative scenarios, and also to see that sometimes it's not that difficult to implement such algorithms and to test these algorithms. And finally, we will sketch some future direction for adversarial machine learning in recommender systems. So let's start just with a very few information on recommender systems, just to frame the topic. And we start with these two definitions. The first one is mainly focused and mainly related to rating estimation. So we see that the recommendation problem here is reduced to the problem of estimating ratings for the items that have not been seen by a user. So what we want to do is to predict a possible rating for an item given the previous interaction of the users with the system. So we consider all the items the user have interacted with in the system, and by using this information that we call user profile, we try to predict a rating for an unseen item. So here the focus is on rating prediction, but if we look at the second definition, this is a more general definition, and here the notion of utility is somehow introduced. So in this case, we see that recommender systems are software tools and techniques providing suggestions for items to be of a use to a user. So here the notion of utility is introduced, and we can easily see that in this case, by using this notion of utility, we can also move, we can also shift the problem from a rating prediction problem to a ranking problem. So in this case, by considering this utility function, we can compute a ranking of items which are likely of some interest to the user. This is from a mathematical point of view, this is the problem. So these are the main elements that we do need to formulate the recommendation problem. So we do need a set of users, a set of items, and an interaction matrix, a user item matrix, where we have all the interactions between user and items. By using these three elements, what we are going to do is to compute this items that maximizes the utility for a specific user. So that's why we are considering this maximization. We're considering this maximization problem. Within this formulation, we are not considering side information such as description of the items, multimedia information related to the item, reviews, and so on and so forth. But it can be actually a part of the formulation. This is the very basic formulation. So related to the rating prediction problem or to the ranking prediction problem, we have to remember that for rating prediction, we can have a loss function. So we can have something that is very useful and that we do need in any machine learning problem. And so in this case, we can define that this is the loss function for matrix factorization algorithm. And in this case, we have that we have, of course, a rating prediction loss and the regularization of factor as for all the machine learning problems that we know. And the same is for ranking. No, so for ranking, we can use point-wise, pair-wise, or list-wise ranking loss. In this case, we see the representation of BPR as a pair-wise ranking loss, where the aim here is to increase the distance between positively rated items and the negatively rated items. Okay, but the main point in showing you these two functions is just to let you understand that also in this case we have loss functions, and also in this case we can work on this loss functions. Okay, so this was, as I promised, this was just a very few slides to introduce the recommendation problem, to give you an idea of what a recommendation problem is, in case this is the first time that you stumble upon this kind of problem. But which are the motivation behind this adversarial stuff, this adversarial machine learning for recommender systems? Well, everything started with a panda, and this is the iconic problem that is presented when we talk about adversarial machine learning, basically. And this is a quite interesting problem. So, sorry. So, if we look at the image, which is at the left-hand side of this slide, we see that, this is an image of a panda, and if we have an image classifier that's able to classify images of pandas or animals, generally speaking, we can train this classifier such that given this image, we have a label, which is panda. The point is that we can add to this image some adversarial noise such that by adding this noise to the original image, we have the image that we see on the right-hand side of the slide. And if we look at this image, well, to me, it is exactly the same as the previous one. I cannot see any visual difference between the original image, and the new one. But the point is that if we give this new image to the image classifier, right now this image is classified as a gibbon. So by adding some well-engineered noise to the original image, we can make a machine learning system misclassify the original image. And this is a serious problem. So we can easily understand how this problem could be serious, for example, for autonomous driving. So if we add some adversarial noise to some signal, so this signal can be misclassified. But the point is that this misclassification is robust against the distance that we have with respect to the distance to the signal, and also is robust to other, for example, to the orientation that we have of this image. So, and generally speaking, this is quite robust with respect to some quite usual geometric transformation of the image itself. So this is another example just to give you an idea that, again, if we look at this adversarial perturbed signal, as human, we cannot see something that is harmful, but at the end, if we look at the result of the classifier, so this signal is classified as a stop signal, and this can be a problem. So how is this related to recommender systems? Well, for example, we know that there are recommender systems that work on also on images that are provided together with the items. So we know that we have some visual aware recommender systems that compute the similarity between between images connected to items. So if we work on these images, we can fool the recommender systems. And for example, this is something that we proposed. This is an algorithm that we proposed last year. And by using an adversarial attack, we can push items in the highest part of the ranked list, even if this item should even not be within the list, within the top end list. Okay, so by changing in an adversarial way the original images, we can attack a recommender system. So there is clearly a failure in the machine learning systems that we use. There is something that is not really clear. There is something that we have to consider, and there is something that we have to take into account very carefully. But what is the origin of such a failure? Well, if we look at the literature, there are this interesting discussions that we can find in this paper. So, for example, this is one of the first paper. This is one of the first papers on the topic. It is a paper published in 2014, and here what we can see is that the message is quite strong, because they say that we found that adversarial examples are relatively robust and are shared by neural networks with varied number of layers, activations, or trained on different subsets of the original of the training data. So if we look at this original sentence, we see that it is not a matter of the number of layers. This is not a matter of the activation functions. It is not a matter of the subset of the training data that we consider. But if we look at the second sentence, this is something even stronger, because what they say is that if we use one neural net to generate a set of adversarial examples, we find that these examples are still statistically hard for another neural network, even when it was trained with different hyperparameters or when it was trained on a different set of examples. So the point is that once you generate an adversarial example, so the same example can be used to fool other machine learning systems that are have been trained with different hyperparameters and even on a different set of examples. So it seems that the point is within the data. So the main point here, the focus is on the data. But then we have this other interesting paper published in 2019, where they say that adversarial examples can be directly attributed to the presence of non-robust features, which are features that are highly predictive, yet brittle and incomprehensible to humans. So what's the point here? The point is that humans have a role in this problem, in this adversarial machine learning stuff. So we cannot work with this machine learning algorithms and approaches without considering the humans within the loop. So at the end, they say that this perspective establishes adversarial vulnerability as a human-centric phenomenon, since from the standard supervised learning point of view, non-robust features can be as important as robust ones. Okay, so it is now we do understand also the title of this paper, where they say that adversarial examples are not bugs, they are features. Okay, so we do understand that other elements should be put within the equation at the end. But more practically, where does this problem come from? Well, if we look at this paper published in 2018, we see that usually when we train our machine learning systems, so we see the assumption is that the inputs X are usually assumed to be all drawn independently from the same probability distribution at both training and test time. This is an assumption that we usually do with our machine learning systems. But the point is that such assumptions rule out the possibility that an adversary could alter the distribution at either training time or test time. So the point is that the point here is that we can alter this distribution, this probability distribution of the data either at training time or at test time. So, and we can change this probability distribution. And this is the point. So if we move out of this assumption, then we start to understand where this adversarial problem comes from. So what is the idea? The idea is that we do know that when we train a model, we have a decision. So consider that a typical classification problem. So we have the decision boundary of the model, but we know that this decision boundary is just an approximation of the actual one. Okay, but this approximation leaves some room for adversarial examples. So in this case, as you can see, the red line is the model boundary, while the yellow part is the actual boundary of the data. And we see that there is room within these two boundaries to add something that are not so clear, that are part of that are within the decision boundary, but that are outside the actual data, the boundary of the actual data. And so the idea is to push, this points across the boundary. So this is the idea. This is the the point with creating this adversarial samples. Okay, so let's start now talking about the foundations and of adversarial attacks, and we start by defining a taxonomy of adversarial attacks with respect to different point of views. So we start with attacks timing, and we see that we can attack a system at training time or at inference time. Okay, so in the first case we talk about data poisoning, while in the second case we talk about evasive attack. So as we can see in the picture on the right hand side of the slide, we see that with data poisoning, what we do is to move the decision boundary of the model. Okay, so what we do is to change somehow the boundary of the model such that a point that was previously classified as red now is classified as green. While with an evasion attack, what we do is that we leave the boundaries. So we don't work on the model, but we don't work on the model at training time. But once the model has been trained, we can create samples such that they move across the decision boundary. Okay, so depending on the time where we design this attack, we have data poisoning or evasive attacks. So this is basically the literature in a poisoning attack, and it is very interesting that the very first paper has been published in 2012 by Battista-Biggio, and this paper mainly relates to super vector machines. So we are in the realm of binary classification, but also in the recommender systems literature, we already know that there are many approaches and algorithms for attacking the recommender systems, but most of these approaches before the adversarial learning era were based on shilling attacks. So in hand engineering poisoning, so in handcrafting this adversarial examples to attack the recommender system. Going back to this taxonomy of adversarial attacks, we have this either point of view, so we can classify attack and defense strategies with respect to the attacker's knowledge. So we can have white box, gray box, and black box attacks depending on the knowledge that the attacker has on the system. So if the attacker has a complete knowledge, so it has access to the parameters, it has access to the training data, it has access to all the elements of the system, then we say that we are in a white box situation. On the opposite side, if the attacker does not have any information about the model, so we are in the black box situation, and usually in this black box situation, the attacker tries to infer the model by asking queries and looking at the replies by the system, and by collecting all these replies, then the attacker tries to hypothesize the nature of the model, and then once the user has this hypothesis, then the user can start the attack. And of course, in between we have a gray box attack where the user has some information about the model. And finally, we have the attacker's goal, which can be classified as a targeted attack or as an untargeted attack. So in the first case, we have always talk about classification. We have that the attacker wants the system misclassifies a sample, but the misclassification must be in a specific target class. So the attacker wants that the misclassified example must be classified with a specific label which has been decided by the attacker. On the opposite side, we have an untargeted attack where the attacker just wants the example to be misclassified and doesn't care about the final label of the example. Okay, so how all this stuff can now be a model in a machine learning way. So we talk we talk about supervised learning. So we talk about a typical classification problem when we want to minimize a loss function. So we want to find the value of the parameter such that we can minimize this loss function with respect to the parameters omega, an input x, and then output y. In an adversarial perspective, this is the problem. So in this case, we want to find a perturbation such that this perturbation maximizes the loss, but at the same time, this perturbation must be as small as possible. So the point is that we have this perturbed input where we have the original input plus the perturbation, and we want that the loss function with respect to this perturbed example must grow, given that the norm of the perturbation is lower or equal with respect to a given epsilon, a given value epsilon, which we call perturbation budget. Usually this value of epsilon is quite small, and algorithms that aim to find such adversarial perturbation are what we call adversarial attacks. So this is a possible framework for adversarial learning. So, for example, we have an image representing the number 1, and we want to add some adversarial noise to this image such that this image is misclassified, for example, as 4. So what we can do is to look at the model. So, for example, compute the Jacobian of the model such that we have an indication about the sensitivity of the model. And given this indication that we have, we can select the perturbation, add this perturbation to the input, and check what happens with the classification of this perturbed input. If the input is correctly misclassified, then we are done. Otherwise, we give a feedback. We give a feedback to the first step basically, and we change this perturbation. And so we analyze again this direction, the direction of the sensitivity estimation, and then we continue iteratively until we are able to find the right perturbation to have the image misclassified as 4. These are the main methods that we have to attack computer vision systems. So we present these methods in computer vision systems because they are at the basis of attacks that we can have in recommender systems, and also because in the computer vision domain, these attacks have been presented and have been discussed more. So we have that the first one is this LBFGS, which uses this algorithm to solve the problem with the linear memory requirement. Then we have the fast gradient sign method that we will discuss a bit more later, that focuses on the gradient of the loss function to work on the constraint problem that we have presented before. And then we have this very strong attack, which is the Carlini-Wagner, which extends somehow the first one and is also able to defeat the defensive distillation, which is something that we are going to see. And then we have also this other two attacks, which are the JSMA and the deep fool attack. But they are just some of the attacks that we can find in the literature. So just to give you an idea on how fast gradient sign method works. So let's take a look at this simple example. So we have the original input x0, and then we have that we add to x0 this perturbation, which is delta adversarial. And then we have this new x prime, which is the perturbed input. So what happens if we compute the inner product between the values of a set of parameters and the perturbed input? Well, what happens is that we have these two terms. The first one representing the original inner product between the parameters and the input, while the second one is the term representing somehow the effect that we have by adding this perturbation. So the point here is that we want to maximize this factor, this perturbation factor, but at the same time, we want that the perturbation must be as small as possible. A possible idea is that of setting this perturbation equal to the budget, the perturbation budget epsilon, and the sign of the vector omega. So why this could be a good idea? So if we look at what happens in this case, we see that if we consider the perturbation as the sign of omega, we see that this product is equal to epsilon, the perturbation budget, times the sum of the absolute value of all the elements that we have within the vector omega. So if we consider m as the average of these values here, we see that this term grows as epsilon times m, which is the average of these values, times n, where n is the dimension of the vector omega. So this is quite interesting because we see that even if this epsilon is quite small, so even if this perturbation budget is quite small, we have that this term grows linearly with n. Okay, so also in the case where epsilon is a small value, if we have a large number of parameters, for example, represented by omega, so we have that the influence of this perturbation grows linearly with the number of parameters. So how this intuition is put within fast gradient sign method? Well, the point is to use the gradient, and in this case we linearize the loss function around the fixed value of omega, and then in this case we get an optimal max norm constraint adversarial perturbation. So what happens basically is that the adversarial perturbation is computed as this epsilon, which is something that we fix at the beginning. So we decide that our perturbation budget is fixed, is 0.1 or it's whatever value that we want to establish, and then we multiply this perturbation budget with the sign of the gradient of the loss function. So with respect to untargeted and targeted adversarial attack, so also from a machine learning perspective, we can model this the untargeted adversarial attack as this problem, where we have that we want to minimize this perturbation such that the classification function classifies my perturbed sample with a label which is different from the original one, or this can formulated as a constraint optimization problem or as an unconstrained optimization problem. These two formulations are equivalent, and of course we have the targeted adversarial version, where we have that the label is specified by the attacker. And also in this case, we can have the constrained version and the unconstrained version. But we don't have just attacks. We can also have countermeasures for these attacks. And specifically, we can have proactive countermeasures and reactive countermeasures. In proactive countermeasures, what we try to do is to model our, is to design our models such that they are robust against these attacks. And specifically, we will see adversarial training, defensive distillation, and robust optimization. And of course, we can also have reactive countermeasures, which are measures that try to detect attacks, to reconstruct the input, or to verify the network. So this is what we have for adversarial training. So in adversarial training, what we do is that we add this regularization term in our loss function. And in this case, this regularization term considers somehow exactly the same idea that we had for the FGSM attack. So what we do is that starting from a certain number of epochs, we add this adversarial regularization term, and we see that after we add this this adversarial regularization term, it can be shown that the final trained model is robust against attacks. But also, what is quite interesting is that, as shown in this paper in 2017, if we add this adversarial training, so we also get better results in terms of accuracy of the final model. As for the defensive distillation, uses the notion of distillation, which is used for model compression, to train a model which is robust again, also in this case, against attacks. So the idea here is to work on the last layer that we have in a deep neural network, you know, the softmax layer, where we have that usually in our softmax layer, we have this value of temperature set to 1, such that we have a clear classification vector at the end. So the point is that the main idea behind the distillation, generally speaking, is that we put this value of temperature to a higher value. So for example, the value going from 40 to 50, for example, such that the final vector is a smoother vector, but at the end it's also able to discriminate and to classify the samples. So this is the way it is. This is the way it is used for model compression. So at the end, what we do is that, given a very huge and big deep neural network, which is pre-trained, we use the final probabilities that are computed by the softmax layer as the new labels for a student network that is trained again. Okay, so this is what is what is done with the distillation for model compression. So how this distillation is used then for as a defense strategy? Well, what we do is something like this. So we have the initial network where we set the value of the temperature to a high value. So as I was telling you before, a value which is between 40 and 50, and then we train this network, and we use these probabilities as the new labels for the same network retrained, but with the temperature set to 1. Okay, so so we use this initial. We use the same network initially to, let's say, compute this new labels, and then the same network is trained again by using these new labels, you know, to classify with respect to these new labels with a temperature equal to 1. And it can be shown that in this case, this approach works very well as a defense strategy. Well, finally, we can define the robust optimization as this min-max problem, where we have this, as usual, we have our loss function, but we can have this, unique problem, unique min-max problem, where we want to minimize the loss function with respect to omega, with respect to the parameters, but at the same time, we want to maximize the same loss function with respect to the perturbation. Okay, so in this case, when we have this min-max formulation, we have this notion of robust optimization. Okay, so this is everything related to adversarial machine learning for attack and defense. And at the end, we see that we have this game between an attacker and a defender. So we have the attacker that tries to fool the machine learning system, and at the same time, we have the defender that tries to behave correctly. In this respect, we can frame generative adversarial networks. So also in generative adversarial networks, we have this attack-defense game, which is also in this case defined as a minimax game. So what happens in this case is that we will see that we have two networks playing this minimax game. So there is a network trying to fool a classifier, and the classifier trying to learn how to detect this adversarial samples, basically. So you may know that generative adversarial networks are a very successful application in many different domains and for many different use cases. So, we can use generative adversarial networks for super resolution, for image-to-image translation, text-to-image translation. So we can use this networks, this architecture for many generative tasks in a very successful way. So how do generative adversarial networks work? Well, when we have a normal classifier, we see that given an image, that the classifier is able to say, okay, this is a lion or this is not a lion. Well, what happens in a GAN is that we have these two networks. We have the generator and the discriminator that play, as I was saying before, that play this game. So the generator tries to generate samples which are as similar as possible to real samples, and the discriminator must be able to discriminate between real samples and generated one. So in the end, the generator maps this Gaussian random noise to fake data to fool the discriminator, and at the same time, given the input, the discriminator must be able to say, okay, this is an input coming from the generator, or this is an input coming from real data. And at the end, we have this game again, where there is someone trying to minimize the loss, where there is someone else trying to maximize the loss. Here we have the original formulation of the problem, where J is the negative the generative log likelihood of the for the network. And then also in this case we have this minimax game. Okay, so everything can be modeled by using this loss function. And again, we have this minimax game where there is someone trying to minimize this loss function, and there is the other network trying to maximize the loss function. So this is the reason why we have this generative adversarial network are also within this tutorial, because they share this idea of this minimax game coming from the idea of, okay, I'm trying to fool you and I'm trying to detect you. Okay, so that's it for the first part of this tutorial. So I really hope that you got the main intuitions and the main idea behind the adversarial machine learning. And then the stage is to Yashar to continue on adversarial machine learning with a specific focus on recommender systems. Please, Yashar.
Sure. Can you see my screen?
Not yet.
Okay, just a second. Now?
Okay, now we see the whole screen.
Is it okay?
Yeah, now it works.
Perfect. So thank you very much, Tommaso. So the second part of the tutorial would be focused on adversarial machine learning for recommender system. And the difference would be that everything that presented in the first part, we will see the application of those concepts for recommender systems. So everything we talk about in the following slides would be directly related to recommender system. Okay, so milestones in recommender system model developments over the last few decades can be found in this figure. We can identify two main eras as represented with different colors. Recommender system using classical machine learning techniques, the one on the left, and recommender system using an adversarial machine learning paradigm colored by yellow and by purple on the right, where these approaches start emerging in the Rexis community after 2016, and they're still going on. Of course, both trends are still emerging, but the starting point of adversarial machine learning was around 2016 and 17. So the first era is the era where the main effort of research community was concentrated on the golden objective of maximizing recommendation accuracy and beyond accuracy aspects such as novelty, diversity, and catalog coverage. So the main goal in this era was to build machine learning models on top of recommender system that can learn any signal available in user item interaction data together with side information in order to provide better recommendation quality. And we can classify these methods according to collaborative filtering and feature-based method or collaborative filtering using side information. And as this community knows well, over the last basically years, recommender system community has devised and proposed various recommendation models, which we can divide them based on several perspectives, such as memory-based, model-based, and in particular of those model-based techniques, deep learning techniques, and techniques using graph-based structures. The second era, basically, is the era of where adversarial machine learning basically started emerging. So we can identify two main classes of basic applications of adversarial machine learning for Rexis, as was pointed out in the first part of this tutorial, which are adversarial examples generated for a security purpose of recommender system. And the second part is the learning paradigm used in generative adversarial network. So we consider the first part as the principal application of adversarial learning, at least for this tutorial, and the second part, a derived topic, basically based on the same learning paradigm used in adversarial machine learning. So the first part would be presented by me and my colleague Felice Antonio Merra, and the second part on generative adversarial network would be presented by Vito Anelli. Okay, so let's talk about adversarial attack against recommender system. Adversarial attack against recommender system can be studied based on three main dimensions. First, the adversarial sample generation. The adversarial sample generation can be hand-engineered or machine-generated. Hand-engineered attacks were the older type of attacks in which the goal was to heuristically, for example, generate or put user or items in the user item interaction data with the goal that such, let's say, injected profiles into user item interaction data can alter the recommendation result toward a specific desire of the attacker. And machine-generated attack, however, could be based on if they're used to generate fake user an item or to create adversarial noise. In the community of recommender system, these three categories of this, attacks are known as hand-engineered shilling attacks. Also, they're called profile injection attacks, which started from 2002, their emergence, and still basically there are works on this topic published at major IR and Rex's community. The second part is machine-generated poisoning attacks, starting from 2016 until now. And finally, adversarial attack, which is the main, let's say, focus of our tutorial at ECIR. And here are a few pointers to related attack and defense strategies based on these categorization that you can find in this slide. The second dimension is adversarial component. Adversarial component can be chosen as input data or internal of recommender system models. Input data could be the user item interaction data, like the rating, user content and attributes, like the reviews user puts or the images he shares and others, item contents, and finally, fake user and items added to the system. Recommendation model, however, basically, we can identify the embedding or the latent factors learned by an optimization framework of the machine learning model during the training. Okay, so this is the second classification point of adversarial attacks against recommender system, or generally attacks against recommender system. Finally, as was mentioned by Tommaso in the first part of the lecture, we can identify attacks based on the attack timing. We have train time attacks and inference time attack. It is interesting to note that the previous attack that we mentioned, hand engineer shilling attack and machine learned data poisoning attack, from this categorization, from this perspective, could be seen as poisoning attacks because they occur in the train time. Inference time attack are also known as evasive attack because the idea of the attacker at the end is to evade or escape the decision made by the learning model, classification, or recommendation. The best example of inference time attack are adversarial attack, which will be presented in the following slides. And also, we can note that adversarial attacks could be also used at the train time, as we will present some of the examples of that in Rexis. Finally, it might be interesting to consider between these different terminologies, profile injection and profile pollution, which also is used in some of the works at Rexis or IR, where here the term pollution is used because at the end of the day, there is a noise factor that is added to the data, okay, in such a way that it pollutes basically the system. Whereas in this case, there is a user or a user profile added to the system, so the term profile injection. Okay, let's talk about these main attack strategies. Let's start with the first one, which is the hand engineer shilling attack. As shown in this figure, given a URM, a user rating interaction data, where some users have rated a couple of items, so movies, the goal is to add a number of fake users, okay, so this is done by the attacker, on the system with certain rating profile, so that at the end of the day, these rating together with the original data could be harvested to push or to guide the recommendation into certain direction. So for example, you can consider a scenario where a competitor company would like to push certain items, okay, into the recommendation list of most users. So to enhance the recommendationability of a particular item or class of item, where The second case could be more nasty, let's say a desire where this competitor would like to nuke your items, basically to demote the items that your company is producing. The way these attacks are conducted is based upon definition of a rating profile, which defines this fake user. Different attack strategies are classified based on how they assign rating to different sections of this user profile. So this user profile is divided into a number of non-overlapping segments, each one with its own goal. And basically, we can name off popular collaborative filtering attacks based on this paradigm, named as random attack, popular attack, bandwagon, and love-hate attack. Readers are invited to the following survey by Jones, named Shilling Attacks, for further information on this category of attacks. Here's an example of a work on the application of shilling attacks, which we presented at ECIR 2000, where this work focuses on the attack side of shilling attacks, with the main novelty in which we explored the relationship between a number of data characteristics, such as a sparsity or user rating matrix, okay? The user rating matrix size or shape, with a target basically label, in this case basically defined to measure the success of the attack. So simply speaking, basically we used a regression model in which Y represents the success of the attack measured by delta hit ratio, which is the difference between hit ratio after and before the attack, and X reserves the basically the data characteristic that we basically extract from user rating matrices. So by building or using a large number of data sets used in the Rexis community or artificially generated with different data characteristics, we explore the relationship between data characteristic and the success of the attack. And one of the interesting insight about this work was that we realized that out of these very common data characteristics, some of them, like a sparsity and the size of the URM, in fact, can have an impact, either reduction or increasing the impact of the attack, while some of the others, such as a standard deviation of rating, do not have any impact or any significant impact on the outcome. So the take-home message of this study is that if you want to basically understand the relationship between the data set that you're building, you're training your model, and the success of the attack, consider some of the data characteristics more important as the other one. Another example we can mention of this work, basically presented at Neurocomputing Journal, called SVMTIA, where different from the previous work, this work focuses on defensive side of handcrafted shilling attack. And basically, the authors propose a detection mechanism. So detection is one of the techniques for bringing robustness to your system. And the way this is done is by basically differentiating malicious user from normal users. Okay, now we come to the second type of attacks, which are called data poisoning optimization attack against recommender system. So the first question is, what is the main difference between shilling attack and data poisoning optimization attacks? The point is that shilling attacks, they are handcrafted, they are hand engineered, okay? They are heuristically designed by the attacker, okay, with certain knowledge that we can assume the attacker have about the underlying data or the model, okay? However, no optimization procedure is there to basically learn this profile composition of the user. So in data poisoning attack, again, recommender system, instead, a machine learned optimization framework is built to learn the optimal profile of the user based on the attacker utility and the other information available. So specifically in the Rexis community, this type of attack, data poison optimization attack, can be used or are used for different type of system, predominantly on factorization-based models like matrix factorization or matrix factorization DPR, reinforcement learning, graph-based, and Canyon. Readers are invited to take a look at the book chapter we wrote at basically on recommender system, the 3rd edition, which I think will be available in a couple of months for further information on data poisoning optimization attack. Finally, we can note that data poisoning optimization attack different from normal classification, let's say, or classic optimization method for recommendation, do need to have further information. Okay, which are these further information? They are the attacker utility, so how the attacker defines the success or the usefulness of the attack. Okay, the target recommendation model, and finally an optimization model that combines this information together. Here is an example of data poisoning optimization attacks. So Tommaso mentioned one of them. Basically, was one of the leading works in the first talk, and this is another example which is focused on deep learning recommender system model. So simply said, as you can see in this chart, the goal of this work is to manipulate a deep recommender system such that the attacker chosen target items could be recommended to many users. So from this perspective, it has a clear similarity with shilling attacks. However, as you can see from the model, the way it is done is based on training. Okay, so the attacker uses the hit ratio as the measure or the approximation of the hit ratio to measure its utility, uses a training procedure called poison training to create the composition of this user profile. So basically the filler items within this profile, which at the end would define that user profile. Okay, so we can see this automaticness of the profile injection in this paradigm, and then the different information that it is assumed the attacker should have. Okay, so we come to the main part of this part of the tutorial, which is adversarial machine learning for security of recommender system. As mentioned in the first part, one of the major areas where adversarial machine learning is used is machine learning security. The core idea is that machine learning is effective for IID data, which means all the data are drawn from the same distribution in the training time. These samples are independent from each other. So if we want to make machine learning model secure, that basically so that the attacker can intentionally cause or cannot basically intentionally cause the machine learning model to produce results according to the attacker desire, we need to relax these assumptions. Okay, in fact, adversarial machine learning or adversarial examples, sorry, let me correct this word, adversarial example taught us that simple word, real word modification are sufficient to break the IID assumption. And on the defensive side, we don't have a full solution yet, but so far, one of the best solutions has been adversarial training. And we're going to talk about this more in the following slide. The idea behind adversarial training is to look for an equilibrium for a game where machine learning model tries to minimize the error as it classifies its inputs, while the attacker tries to maximize the failure of the machine learning model. How can we generate adversarial example? To do so, we define adversarial noise according to this formulation, which is maximize my loss function while adding noise to the model parameter. Okay, and this noise is epsilon constraint. So epsilon defines the budget or the power of this attack. Okay, And the calculation of adversarial noise can be approximated by the subsequent equation, as you can see in this slide. Okay, so what are the differences between REXs and image classification or other supervised learning tasks where adversarial examples were created? In the beginning, where this topic was introduced in basically the REXs community, these two problems were identified. So as you know, and as it was mentioned, adversarial examples or adversarial noise, we can call them, were originally created for supervised learning tasks for such as image classification. However, unlike images, which have continuous nature, the data has a continuous nature, the input to recommender system are discrete. So for example, rating or user item IDs, okay? So gradient-based approaches are not suitable to calculate adversarial noise for basically this kind of data. The second thing is, how can we model the notion of unnoticeable? Because in the image domain, one of the ideas of creating these attacks is that they remain hidden from the point of view of basically viewer, okay, the user or the designer, basically. But what does the notion unnoticeable mean for recommender system, where you have at the end of the day a bunch of data? Okay, so we're going to talk about these more in the following slide. Let's start with the first question. Given that we have generated this noise, okay, this adversarial noise, how can we add these adversarial noise, or basically where they could be added in the design space of recommender system? So adversarial noise are typically in recommender system added to the model parameters, which are usually latent factor embeddings, basically of the system. Okay, and according to basically the survey that we published at Async Computing Survey recently, we identified in the literature 3 main positions where adversarial noise basically have been added. They are the embedding of the collaborative filtering model, so like matrix factorization, the side information of items such as the VBPR, or side information of users. Okay, so basically here we can point the viewers to one of the pioneering works basically on defining this adversarial noise against recommender system, which was proposed by Xiang and He, named Adversarial Personalized Ranking for Recommendation. This work is also known as APR in the literature. So simply speaking, what the authors did in this work was to, first of all, define this adversarial noise based, or to be added to the model parameters of matrix factorization BPR. So BPR was the objective and matrix factorization was the predictor, which was used to join these together. And it was the core optimization framework, basically BPR, based on which the adversarial noise and adversarial training as a defensive procedure was defined and conducted. Some of the interesting insights on the results the author present was first comparison of adversarial noise versus random noise, because this is the first question that comes to your mind. Okay, now that you have created these intelligently created noise, how do they compare compared with random noise? The second question is on the defensive side, which, given this adversarial noise, is there a procedure where I can reduce their impact? And the authors show basically the impact of adversarial training on basically reducing the effects of adversarial noise added to the data. So let's start by analyzing the results. On the attack side, basically, as we presented before, the author applied the embedding on the user and item embedding of matrix factorization, which is used as the predictor in matrix factorization BPR. Okay, and again, these perturbations were basically epsilon constraints. So they had a budget, and under that budget, which we can see in this table, the author investigated the impact of adversarial attack. So for example, as you can see in this table, given for NDCG at 100, it was shown that on Koala dataset, when we change the epsilon from 0.5 to 2, we can reduce the quality of the recommendation from -26% to -78%. And this is the impact of the adversarial attack, which, as you can see, can be devastating based on the strengths of the attack. So even with a small budget, we can see almost 25% or 26% has been reduced on the original recommendation quality. And this is something that can definitely impact the end user as a recipient of these recommendations. The second question, as we said, is about, okay, now that I'm creating this adversarial noise, how do they compare with respect to random noise? And as you can see here in these curves, for a given data set on Pinterest, the author showed the large difference between adversarial noise and random noise when added to model parameters of Bprmf. So, for example, for a given epsilon, as presented here, the adversarial noise was able to reduce NDCG by -21%, whereas random noise could only reduce it by -1.6%. And this is a difference about 13 times. So this is an indication that these attacks are doing something very important with respect to the outcome of the recommender system, which is user satisfaction. So now that we have these insights and these results, the question is, how can we bring robustness? How can we protect our system, our recommender system against them? And as presented again in the first part of the lecture, basically there are two main strategies. One is to building or increasing robustness through learning, and the other one is detection. So detection means we can detect adversarial noise from normal or clean samples, and through that we can avoid using those samples. So we are going to focus on the first part, increasing robustness, and on that we are going to talk about robust optimization. In particular, robust optimization could be classified according to adversarial training, robust gradient descent, and certified robustness, where adversarial training or adversarial regularization is the main or the only popular approach in Rexis, so that would be the main focus of our talk. However, readers could find these very interesting lecture notes for further information on application of these techniques in a general machine learning setting. So, adversarial training basically is optimizing the machine learning model in presence of both noisy and clean samples, and then regularizing the cost function to account for the adversarial term, as you can see on the right side. So here, Jx basically theta is or delta is the original loss function, and the right term is the adversarial term. Okay, so the idea is by regularizing the loss function based on the adversarial term, we can account for basically the impact of the attack and try to minimize this overall within the recommender system model. Okay, so at the end of the day, the complete training process, as you can see in a Rexis framework, is given based on a min-max gain between the machine learning model. So in this case, J is a BPR loss function, and the adversarial components. Okay, so while the main model tries to basically tries to minimize the loss, the adversary tries to maximize this loss function. So they are trained until they reach an equilibrium point. So how did this approach work for APR? The authors basically showed the differences of leaving, let's say, let's say adversarial personal ranking, which is when you use basically this defensive strategy based on adversarial training, and without it. So as you can see here, for example, for a given epsilon, for a small epsilon of 0.5 on Guala dataset, we can find a difference of about 10 times. So minus 26.3 is the original when the system is under attack, and APR when it is robustified based on adversarial training. So these are very interesting results because they can show not only the adversarial noise itself can have a devastating effect, but we have, even if not ideal, a training procedure and based on a modified optimization framework, which is called Adversarial Regularization, that can gain back some of these lost values on basically the loss function. Okay, and here you can witness when we go from left to right the differences. So, for example, on Guala dataset, for a higher epsilon, we had a huge basically decrease on the loss, which was minus 78%, and that goes down to minus 29.2%, which is a difference about 3 or 4 times. And these results generally can show how much defensive procedure, for example, in security-sensitive applications, they can protect citizens, they can bring robustness to the system. But then another question: this system is tested now on noisy samples. The question is, if I test this system basically using adversarial training instead of the BPR, okay, so adversarial training was the extension of BPR, how does it work on clean samples? How does it work on clean sample? We can see it is named as generalized recommendation performance, okay? So what is the generalized recommendation performance? And very interestingly, the authors could show that not only the adversarial training can improve the robustness of the system when they're under attack, but also their generalized performance. So for example, for Guala datasets, as you can see in the first case, the authors show an improvement that can range from 3% to 400% based on which recommendation model you use. Okay, so it means for different recommendation models, even if your system is not under adversarial attack, if you use adversarial training, your general recommendation performance could be improved. And this was something nice for the REXIS community. We would like at this point to point the reader to an extension of this, the APR attack from a perspective of the iterativeness of adversarial samples. So this work was basically recently accepted at FLIR's conference, in which basically we proposed an iterative basically attack starting from the original perturbation that was created by previous methods, namely FGSM, and then basically that was used under the same recommendation setting or evaluation setting to see if these attacks, basically, which are basically clips, if they have a different impact with respect to normal attacks. So basically, these iterative attacks could be seen as an extension of single-step attack like FGSM, which were commonly used in the Rexis community. And one of our main goal was to investigate the efficacy of iterative attack on matrix, basic recommendation system models. And here are some insights about the results which we obtained. And generally, what the results were telling us is very interesting. Basically, they are highlighting the fact that iterative attacks are much stronger attack compared to single-step attacks. So consider the same framework that we mentioned before for generating these attacks based on that optimization, but you iterate it over and over based on a clipping function that with the goal that you can provide better noise. Okay, so this was done, and it was basically integrated within the Bprmf, and we could show that this iterative attack are so much strong that can basically worsen the recommendation quality to perform as bad as a random recommender system. Okay, and the other interesting insight was that the adversarial training strategy used in the previous work shown not to be effective or very effective for multi-step basically attack. So this work, or this directional work, which we could apply for different type of embedding at different positions within the Rexis framework, could be seen as an extension of a single-step attack, which we presented before by APR, and they are open for further investigation by the community. Okay, at this point, I would like to give you a hint about other positions where these attacks could be applied. So Zheng He and basically on a work basically tailored for visual aware recommender system, investigated impact of this adversarial noise while added to the embedding of the item content. So in particular, the visual content, for example, extracted via a pre-trained convolutional neural network. And this is study, and this direction of a study is very interesting because we at Rexis community generally are, let's say, have been so much collaborative filtering oriented. Okay, there is this general belief that collaborative filtering or user item interaction is the dominant type of information, so that is the type of data that we need to protect. And what this research basically showed is that if you add these content, these embeddings on the content side of the system, okay, basically the VBPR, which is the extension of matrix factorization predictor, we can still dramatically impact the outcome of recommender system. And for example, for a dataset on Amazon and Pinterest, the authors show for a very, very small epsilon, which is 0.2, they could reduce the NDCG at 100 up to 70% or 30%. And this is very, very interesting because it shows from the point where these attacks are injected or added to the system, these noises basically, we could still impact the quality of recommender system quite a lot. And also tried adversarial regularization and managed to show that the adversarial regularization technique is still able to gain back some of the lost performances basically for different values of epsilon. Now, given the interestingness of this topic, my colleague Felice Antonio Merra is going to present you further works that has been done on this topic of adversarial multimedia recommender system, basically for your interest. So thank you very much. I will pass it to Felice at this point.
Thank you, Yashar. I'm going to share the screen. I think that I can share as soon as. Okay, you should stop your screen sharing, Yashar.
Yes.
Please. Okay, now I think I can share it. Okay. Can you see the screen?
Yes.
Thank you. Okay. Good morning or good evening to everyone. And in this part of the tutorial, we are going to present you some further work related to the application of adversarial perturbation on content data. In particular, a class of recommender system that can be really related to adversarial machine learning is the one on multimedia recommender system. Indeed, the adversarial machine learning topic has been firstly investigated in computer vision tasks, and the human imperceptibility of adversarial perturbation on images is one of the first important aspects that was retrieved in the computer vision community. And in the multimedia recommender system, we can have a very similar problem, but at the same time, we have to focus on the personalization task that we have in the recommender system. First of all, the first aspect that we can see is that we need also in this case to change to classify the attacks in training time and testing time attacks. For the case of training time attacks or poisoning attacks, the idea is that we can add perturbed content into a multimedia recommender model such that the classical or normal behavior of a multimedia recommender model is the one in the best case. So in the case where no adversaries or malicious users are trying to modify the behavior of the model. And we will see later some works that investigate this aspect. While testing time attack or evasion attack, the assumption is that the model has been already trained. So there will be no future training of the model. But what we have here is that we are assuming that after the recommender model has been trained, we are changing, replacing images already uploaded in the system with an adversarially perturbed one. In this case, we are assuming that there is no more training, but the new image will be used only at inference time. While in the first class, the poisoning one, we are assuming that the adversarially perturbed product images are injected into the system before the training. So this is an important distinction. As we have seen before, one of the first work related to this type of attacks assume that we can perturb the image of a product to push or nuke a category of items. First of all, what we need to, to, to understand is that in the case of a multimedia recommender system, we have different type of content processing. The state-of-the-art multimedia recommender models like VBPR, AMR, ACF, and DVBPR use basically different strategies to incorporate visual features. And basically, depending on the strategies to incorporate visual features, we can have different type of attacks. In this case, for instance, in the case of VBPR, AMR, and ACF, we have the usage of a pre-trained convolutional neural network to extract the visual features. While in the case of DVBPR, we are going to learn the features inside the personalization task. So the convolutional neural network to extract the visual feature from the images will be trained within the downstream task that is the recommendation. For instance, the pre-trained network used for VBPR is AlexNet. For ACF, we have ResNet 152. So we have this type of choices. While for DVBPR, we don't have this choice because the network is inside the model itself. We have, for instance, 5 convolutional layers. And in this framework that we have presented a few weeks ago, and the paper is under review, we have tested poisoning or training time attacks while changing different combination. First of all, in the first part, we have the adversary.
The adversary, with different attack strategies, can perturb the images by adding that small perturbation, as claimed before by Tommaso, that is basically human imperceptible. And then these images that is still, in this case, for instance, a shoes, a sandal for a human, will be classified by the network used to extract the features, I don't know, as a t-shirt. Because the adversary has perturbed the image such that the image feature extractor component, the number 2, will misclassify the original images as a t-shirt. And obviously, the meaning of the latent features that has been changed will change also the recommendation task. And then in the second component, indeed, we have different approaches to extract features. We have verified both traditional one, but also defended one. And then we have the third component of a visually aware recommender models, which is the recommendation engines that use visual features. In this case, we can have custom image feature extractor component like in DVBPR. We can have a defended or not preference predictor component. So the component of the recommender system that is used to learn the user item preference score, and then the generation of top key list. Indeed, what we have seen is that we are applying a white box attack with respect to image feature extraction. It is an error here. It is the image feature extractor. While it is black box with respect to the recommendation engine. Why it is a white box attack with respect to the convolutional neural network, which is a pre-trained one? Because basically it is a public structure that we have in the mode we have online, for instance, or TensorFlow itself release some pre-trained network that can be used by anyone to change the class of an images by simply adding few perturbation. And we have tested three uh, state-of-the-art attacks: FGSM, PhD, PGD, and Caroline and Wagner. At the same time, we have also explored different defense strategies. We have adversarially trained the recommendation engine using the APR strategies that Yashar has presented before. We have also used adversarial training and also free adversarial training strategies to protect the convolutional neural network to extract the features, as previously described by Tommaso related to the computer vision task. But also we have tested, we have assumed that using an end-to-end approach is basically where we don't have anymore the classification of a classical convolutional neural network would be a defense. And testing all this setting demonstrated that we have security issues in any cases. With the traditional network, we can improve, for instance, in this case, with a simple attack by more than 10%, the popularity of the class of items that you are going to push. But also when we are using training strategies to protect the network, are still not affecting. For instance, with VBPR in an Amazon Man dataset that is really common in visually aware recommender system papers, we are, for instance, doubling the recommendation popularity of a class of items. So it is still an area of investigation where the research question is, how can we protect our model from adversarial poisoning images? And it is something that needs further investigation. Another aspect that we have seen is that these images are, these attacks are very, very effective. For instance, we can move from an item from the 68th position to the 10th with a very human imperceptible perturbation. So we are pushing for of 58 position with a LPIPS value. LPIPS, it is a common metric in computer vision to evaluate the visual dissimilarity of two images. And having a very imperceptible attack, but a very effective attack on the recommendation results. Then we have also another class of works that recently is emerging in the community, which are the test time attacks. This work, which is proposed a black box attack for visual recommender system, has been recently presented at Wisdom 2021 by Rami Cohen and other researchers. And the idea is that we are assuming that the model has been trained and we will not train it anymore. We can replace an image in the system, and how can we replace it in order to increase or decrease the preference score, or increase or decrease its position in the top Q recommendation list. And their approach is to model this problem as a B-level optimization function, where basically they try to identify the minimum number of iterations while perturbing changing a single pixel will change the position or the rank or the rating of the item associated to that image. And in this attack setting, they have investigated three main goals. For instance, change the recommendation position for a specific user, for a segment of user, and for the general population. So the overall recommendation performance. Another work has been proposed by Zuran Liu and Martha Larson, and we will present it at WWW 2021, I think, in the next weeks. And also in this case, we have a test time attack. In this case, we have three types of attacks investigated by the authors: a white box, a green box, and black box attack. In this case, in the case of white box, they are assuming that the images can be perturbed by back propagating the the the, the, the loss function values from the end of the recommendation task back to the image feature extraction. Or in the case of green box and black box, they have a different approaches to model the the possibility to push or nuke an item in the list. But also in this goal, we have the fact that we want to promote or demute a specific item. So basically, we can see that this ER is a very new ER that has a lot of possible open direction that can be explored in this case, that can be both from an attack point of view, because there are still different type of attacks that can be investigated and proposed also with respect to who is going to be attacked, because we can have, for instance, also reliability attacks when the model is not able to perform any type of personalization with respect to all the user in the system. But also an open direction is on the defense side. How can we protect our models by this type of attacks? And also, is only the image domain uh, attackable by an adversary by perturbing the content? Because, for instance, also in the music domain, we are using content, and in this case we have audio files, but also in video recommendation tasks. So the multimedia recommender system is a type of models that can be under attack under different type of adversary threat models. And so we have also other application of adversarial learning, for instance, in autoencoder deep models on factorization machine, but also recently has been investigated are also other type of adversarial perturbation models with other strategies like Carlin and Wagner. And regarding the domain, the most investigated domain are the media domain, the multimedia domain, the product search, and social recommendation. So there are also other domains, I don't know, like the food domain, that is quite uninvestigated and can be under analysis. And so I have already basically presented this possible open direction, and the next section will be the rest part of this presentation will be presented by Walter, and it is related to the gun-based recommendation approaches. Thank you for your attention.
Okay, let me share the presentation. Okay. Do you see the presentation?
Yes,
Yes.
yes.
Okay, perfect. I'll try to do my best to stay in the times because we are almost running out of time. So I'm Walter, and I'll be with you in this first brief introduction to GANs, and then later in the second part of the hands-on session. In the previous parts, we have focused on discriminative models, where the aim is to learn a conditional probability given an input. From now on, we will focus on a specific class of generative models named Generative Adversarial Networks, in short GANs. A generative model tries to learn an unknown generative process that is behind the generation of our original data. In adversarial learning, these kind of models are particularly helpful since they can generalize well and they are able to learn the unknown user preference distribution even in complex settings. For these reasons, these kind of models are widely adopted in recommended systems to improve, let's say, collaborative filtering approaches or context-aware recommended systems or domain transfer or security or even fashion recommendation. Before examining the security application of GANs for recommendation, I need to introduce you how we can produce recommendations using GANs. We can surely start with some pioneer works, such as IRGAN and GraphGAN, proposed in 2017 and 2018, respectively. IRGAN proposed to use GANs to tackle some important information retrieval tasks, like such as the classic query-based retrieval task and the recommendation task and the question answering task. GraphGAN instead was proposed to use GANs, so generative adversarial networks, to improve graph representation learning. To define a recommendation model, we can surely use IRGAN. And here, we need to make an assumption that there exists an unknown stochastic generative process that binds users and items in such a way that given a user, we can generate an item. So now the generator tries to generate items that could be found relevant for a given user. Moreover, we need to make another assumption that there could exist another relation between a user item pair and a numerical value that we call rating. And here, the discriminative function, so the discriminative model, wants to establish if this relation holds or not, and in case the numerical value. GANs were originally proposed by Goodfellow in 2014, and they are typically composed of two different components, the generator G and the discriminator D. Now, the goal of the generator is to capture the real distribution of data and generate adversarial samples that could be able to fool the discriminator. The goal of the discriminator is to distinguish between the generated samples and the real ones. Now, in a recommendation task, we typically do not use classical GANs. We use a specific kind of GANs that is called conditional GANs. Here in the figure, you can see that both the generator and the discriminator are conditioned by the user information. Moreover, if we look at the loss function J, we can see that we have two sets of parameters, theta and phi. And this is because the generator tries to minimize the loss function and modifies its parameters theta to produce better user item pairs. On the other side, the discriminator does its best to maximize the same function and modifies its parameters phi to distinguish the real samples from the fake ones. This computation, this minimax game, is also known as adversarial learning, and it ends when the components reach the Nash equilibrium. Now we can try to draft a training algorithm for GANs in a recommendation scenario. So what we usually do is to initialize the generator and discriminator, and in case we can pre-train them. Then we start with an iterative procedure in which we ask the generator to generate a certain number, let's say K, of items that could be relevant for a user. Then we combine these generated samples with the real ones, and we ask the discriminator to distinguish them. In the end, we compute the loss and we backpropagate it to update the parameters. So given these foundations, now we are ready to look at some representative works about representative, let's say, applications of GANs in a recommendation scenario. But before doing that, we can make a course classification. And if we want to do that, if we want to provide that, we can do it based on the recommendation strategy or the recommendation task. For what concerns the recommendation strategy, we can see that the majority of the works focus on pure collaborative filtering, graph-based recommendation, and hybrid recommendation. For what concerns the recommendation tasks, we can see that the majority of works focus on time-aware application, geographic application, cross-domain, and fashion recommendation. We can surely start with the pure collaborative filtering application of GANs. That is CFGAN. CFGAN has been proposed to address some important issues in IRGAN. And in particular, we can see that there is an important flow in IRGAN. That is a performance degradation that we can observe. And this degradation is due to the fact that the IRGAN generator is producing one discrete item index for each iteration. That is completely different from the computer vision scenario in which we generate with our generator a whole image, let's say a whole vector. So, but why do we observe this performance degradation in IRGAN? Long story short, this is due to the fact that when the generator generates these discrete item indices, this results in a poor sampling of items from the set of available items. And in the long term, the generator begins to produce adversarial samples that are basically identical to the ground truth. So to avoid this problem and basically to avoid misleading the discriminator, CFGAN produces long vectors instead of a single discrete value. So continuous values. And here we can see that this choice has a positive effect. We can see on the left-hand side the performance degradation of higher GAN discriminator over time, while on the right-hand side we can see that this situation does not happen with CFGAN, with the vector-wise implementation of CFGAN. Moreover, the CFGAN authors show us that they are able not only to outperform GraphGAN and IRGAN, but also some other very important state-of-the-art baselines. And finally, we can focus on one of the first security application, or one of the first application of GANs in security recommender systems with adversarial attacks on an oblivious recommender that has been proposed at Rexis in 2019. Here, the goal of the discriminator or the generator is to produce fake profiles that could degrade the top key recommendation performance. And moreover, the authors are able to hide these fake profiles because they preserve the proximity between the item, between the user item interaction distribution in the real data and the user item interaction distribution in the generated profiles. Finally, since the authors do not have access to the recommendation model gradient, they derived a zero-order optimization. They derived a new algorithm based on the zero-order optimization approach. To hide these profiles, what the authors do is to transform the one-dimensional fake profiles, fake user profiles, to two-dimensional vectors to use to exploit DC GAN. And obviously, they could have used any kind of one-dimensional convolutional approach to do that. But they showed to us, and we can see it in the graph in the right-hand side of the slide, that they, with this method, they are able to minimize the Jensen-Shannon divergence over the iterations. To sum up, we have focused only on 3 representative works and 3 representative application of GANs for recommendation, but in the literature we can find more than 50 different possible applications. Just to, and we cannot cover them for the limited time, but just to make emerge some common findings, some trends, we can see that among the generator architectures, we have a prominence of linear models and artificial neural network models. And among the artificial neural network models, we can see that we have a prevalence of autoencoders and variational autoencoders. For what concerns the tasks, we can see that the majority of the works focuses on cross-domain and fashion recommendation. Although the interest in GAN application for recommendation is growing up, several challenges and open research directions still remain. First of all, we can see that the majority of works focuses on movie recommendation. And this leaves all the other domains basically uncovered. And that's a pity because for a recommendation task, we have a lot of domain-specific challenges that could be faced. And that will be interesting to see what happens if we apply GANs in those domains. Beyond these problems, there are a lot of domain agnostic research problems that are still open. For instance, we've seen a couple of solutions for the discrete sampling non-differentiability problem. But are there any other solution out there? Could we find them? And moreover, we have analyzed and we have seen that with GANs, that we can use GANs in fashion recommendation or complementary recommendation. But the fact is that in the majority of cases, we use GANs with items. Is that possible to use GANs also to produce some kind of user personalization? Moreover, we use GANs, usually we use GANs with some type of content or site information. Is that possible to use GANs even with more structured knowledge and with knowledge-aware recommender systems? And more, when we look at the works that focus on the usage of GANs for attacks, we can see that the victim is likely to be a classic collaborative filtering model. But what would happen if the victim is another deep neural network model? It will be interesting. And finally, we think that the times are mature enough and GANs are mature enough to move from offline evaluation to an online evaluation. And there we could see the effects of this kind of recommendation of on real people. And that will be particularly interesting for our community. And I think that I tried to do my best to stay into the time. We went a bit beyond, but I think that could be okay.
Yeah, I think that we have a coffee break of half an hour, and we will come back at I think in 25 minutes.
Okay, I would like to thank you all the attendants, and we will see you again in a moment.
Yeah, we will have an hands-on session during the next part. So
yeah, a couple of hands-on session. So thank you all.
Thank you.
Thank you all.
Hello. I think that we can start the second part of the tutorial. And during this second part, we will divide the next, I think, 1 hour and a half in 3 main sections. In the first one, I'm going to present you an hands-on session where you can basically try to run a bit of code without downloading anything, because it is everything online. Then we will present you a reproducibility framework with the adversarial and generative adversarial network implementation, and Walter will present this part. And then we can have a question answering discussion related to the topic. Okay, I'm doing this introduction to wait a few minutes before the starting. And also Yashar is here. Hi, Yashar. Meanwhile, I'm sharing with you a link, the GitHub link with the hands-on session, and at the same time, I will start also the presentation. Okay. here. I don't know where are the slides. Can you see the screen? I think so.
Yes, we can.
Yes,
Okay,
we can.
perfect. Okay, the first part of this hands-on session will be devoted to the analysis of adversarial learning for recommender system, and in particular, we will explore the implementation of adversarial personalized ranking approach proposed by Xiang and that Yashar has presented before. A very short recap for the ones that were not during the first part. The adversarial robust recommendation framework that we described in our both survey and book chapter uh, provide provides a sort of a general architecture to understand where we can do adversarial attacks. We have seen that we can do it on content data, we can do it on user item interaction like shilling attacks or machine learning optimized attacks, but we can do this type of attacks also on model embeddings. In the case of model embeddings, generally the idea is to study the robustness of recommender models. So when we have a very small modification of the model embeddings, what is the variation of the recommendation? This idea is this robustness idea is useful to understand if, for instance, we are adding a new profile, also not a shilling profiles that will produce a variation of the model embeddings, how much the recommendation can change in a worst case scenario. For this reason, we are going to explore we are going to present, sorry, we're going to present this hands-on to verify how we can implement this approach. To this link, to this GitHub link, you can have this hands-on session that we are going to present. First of all, you can see in this button that there is this launch binder. Clicking on this button, we will wait few minutes to open this Jupyter notebook. Let's give a look to this Jupyter notebook. As you can see, we have this first initial part when we describe what we are going to verify. I think that you will require a few minutes until the full opening of the handbook. So I will present it starting from the presentation while you are waiting for the opening of the program. During this hands-on, we will start from the basic implementation of a BPRMF model. BPRMF model is the state-of-the-art or baseline model for recommendation, where the idea is to train a matrix factorization model in a pairwise setting where the pairwise optimization framework is BPR. Then we will see how to implement the adversarial perturbation proposed by Xiang and Yin, which is a FGSM-based attack, and then we will see the implementation of the defense proposed by Xiang and Yin. That is the APR, Adversarial Personalized Ranking. Adversarial Personalized Ranking basically is an adversarial training strategies or an optimization strategies used to regularize the model in order to be robust to this class of attack. Let's go to the, sorry, let's go to the notebook. Uh, The first aspect that we have to run is the import packages. In this case, we have implemented everything using TensorFlow. We have also a few other methods, utils methods for the execution and the random set. For this hands-on session, we are using a small version of MovieLens. We have taken MovieLens 1M and we have extracted the first 500 user only to make the training really fast and have time to be completed during the presentation. Obviously, you can change it with your data set, with a bigger data set, and also execute everything in local. But for a local experiment, we will see that in Elliot, everything will be already available for you. Then we can download the dataset. All these implementation are in local, so you don't need to download anything. Everything will be uploaded inside this machine on a Jupyter notebook. And we have, in fact, 500 user and 3,000 of items and 73,000 of user item ratings recorded in Mobilence, in this short version of Mobilence. And now we can define the model. Uh, as you can see, before defining the model, I would like to spend a few minutes on describing what is BPRMF. BPRMF, as I told you before, it is a technique that is used to learn the user item embeddings of a matrix factorization model. For a matter of simplicity, we are calling with the P, capital P, the matrix of users, the low rank matrix of user learned for the matrix factorization decomposition, and the capital Q is the matrix of items. And in this case, it is interesting to observe that the same. It is interesting. This is what we have done. We have the same letter also in our implementation. Indeed, you can see here that for the embedding size, which is the D value that we have presented before, we have the low rank of the matrix, which is a 64, but you can change when you're running your code. We set the learning rate to 0.05. We are not regularizing the model to, to be more simple during the evaluation. We will train for 5 epochs with a batch size of 512. Look, BPRMF, the original version is use a stochastic approach, but for a matter of speed, generally it is used in batch. And we are also initializing in this first part the evaluator models. So during the initialization in the init method of BPRMF, we are going also to initialize the model parameters, which are P and Q. And as you can see, P has a dimension equal to the number of users multiplied by the embedding size, so 64, so 500 times 64, and the Q is 3,000, which is the number of items, and 64 again, it is the smaller dimension, the smaller dimension of the composition of the matrix. Then we have also, okay, this is a dummy variable for the learning, but it will not be used. We have the optimizer. In this case, we are using Adagrad, but we can use SGD or whatever optimizer released by the Keras suite. And this aspect here will be described in a few minutes when we are going to verify how to make the perturbation and implement the adversarial perturbation. So we are now on the current slide where we are defining the model. But the next step, as I told you before, is to train the BPRMF model. Let's see the training aspect. So with the run, we are going to execute this batch of code, which is basically the the implementation of the BPRMF class. And then we can start the training. While we are waiting for the training, and you can see here 1 epoch on 5, 2 epochs on 5, and until the end, we can see the code for the learning and the training of the BPRMF model. With the function train, for each epoch, we shuffle the batches and we apply the train step, while in the single train step, iterating across the user input, in this case, we have the the number of batches, we can apply the learning of the parameters. We have seen that the parameters to learn are P and Q. And since we are using a BPR approach, first of all, we get the values for the positive items here. Then we get the values for the negative items. So we have the embedding for positive and negative items. We can measure then the output, which is the preference prediction of user positive item and user negative item, clip the value of the difference, which is the the input of the sigmoid. Then we evaluate the loss. This loss is a TensorFlow form of the sigmoid function that we have in the original BPR implementation. And at the end, with the application of these two functions, the evaluation of the gradient and the execution of the apply gradients based on the optimizer, we can measure the update of the model. So in this way, for the 5 epochs that we have run, the model has been executed, and we have the training executed in 18 seconds. And I think that all of you who is running the code have this training already executed. And now we can measure the performance with the evaluation model, and the iteration is 0.26, the NDCG 0.06, and the area under the ROC curve is 0.81. Obviously, these values are not quite good values because we are using a very small data set, we are using few epochs, and we are not optimizing everything. But again, we will see later how to do it in a more scientific and experimental-oriented way. Now it is the fancy aspect of the adversarial, which is how we are going to measure and build the attack. As we have seen before, what we want to do is to measure this delta, this adversarial perturbation, such that the loss function of the model, that the capital J of X given the parameters and the perturbation, and clip it inside the perturbation budget, will change, will worsen basically the performance of the model, because generally the idea is to minimize this loss function, but here we want to measure the perturbation that maximize it, so the opposite. So the idea is to execute a reliable attack in order to change the performance of the model in a negative way. The attack that has been proposed by Xianggang A is an FGSM-like based-like attack, where we have the measure of the adversarial perturbation equal to epsilon, which is a perturbation budget, and then we have the norm of the the granted measure with respect to the perturbation. And now we can say the implementation. The implementation is presented in the section called execute adversarial attack, the method, inside the code. And it is this one. As you can see, it is basically a very clear white box attack, because it is an attack that has to know everything on the model, and above all, it has to know which are the model parameters that should be the most hidden information. However, uh, even for this type of attack, basically sometimes it is criticized by the community because it is not a real attack, because no one can access the model and vary the parameters, and it is something that I agree to you. However, we have to consider that this attack it is not a shilling attack or a profile-oriented attack, but it is a way to study the robustness of the model. And generally, also in the computer vision domain, we study white box or worst case scenario attacks in order to have defense that if they works in the worst scenario, they should work also in black box scenario when the adversary doesn't know anything on the model. So it is the reason why we have the we are somehow obliged to study white box settings. So in this case, in fact, what we have to do is to measure again with respect to the set of user item in the system, the positive and the negative embedding. We have to measure the prediction that the model at the end of the training is making on this model. So it is again a test time attack. Here we have already trained the model, we clip the value, we measure the loss, but differently from the original training, we are not updating the model parameters, but we are taking the gradient with respect to P and Q, normalizing as we have seen before by scaling with epsilon, and then measure this delta P and delta Q. Delta P and delta Q are the perturbation that we are measuring in a white box way. So we have to know everything on the model. And we have seen iteration 0.26. We are now running a perturbation with epsilon 0.5. It has executed the attack. So the model has been adversarially perturbed at test time, so not at training time. And now we are ready to evaluate the effects. And indeed, the iteration decreased by 20%, from 0.26 to 0.22, 13 13% for the iteration, 20% for the NDCG. So we are effectively worsening the performance, and that is the idea of the adversarial perturbation. So until now, we have verified this first step, also has been presented by the paper that proposed this approach. We have seen basically this aspect here, this table here. One moment. Okay, this one. We have basically reproduced this table here with a smaller dataset. We are now ready to verify what the author proposed to limit the efficacy of this attack. And what they have proposed is the adversarial training, or how they call adversarial personalized ranking. The adversarial personalized ranking is a training strategies or an optimization strategies where what we are going to do is to say, look, while you are training, you have a model that is well performing. At epoch A, you should stop the training. However, when you have a model that is uh, already well performing with respect, I don't know, an accuracy metric or a multi-objective set of metric, we have also to take care that in this situation, we can have model perturbation. So to robustify the model, the idea is to add further training epochs where we use adversarial training strategies. How we has presented by Tommaso before, the adversarial training uses the injection of adversarial perturbed images during the training of a convolutional neural network to make the convolutional neural network robust against possible future adversarial perturbation. Similarly, in the case of recommender system, here we have to add perturbation. So we have to measure a perturbation, add to the system, and then train the system not only by minimizing the classical loss function, but also minimizing the effect of an adversary. And here we have the classical minimax game or adversarial game that we have in the literature of adversarial learning that comes from the John Nash theory of zero-sum game. And basically, it is what we have done in our code. We have to implement this minimax. And let's see how we have implemented, or how we have to implement in TensorFlow, for instance, these strategies. Let's see the adversarial training implementation. The adversarial training implementation, only one epoch to test rapidly what is going to happen, is here. So adversarial training step. We have again a batch because we are doing another step of training. We have an adversarial regularization parameter, which is this lambda here in the formula, is this one. And for each batch, we have again the model embeddings P and Q. We measure the positive and negative score. We clip the results. So here the model, it is still original, and we have the classical loss. So until here, everything is equal to the classical training, and it is this component here. However, now we have to do the opposite. We have to execute attack. So something, so to mimic the adversary that tries to maximize the loss, to break the model. So we measure the attack. Again, we evaluate the inference, but in this case, the inference is evaluated by using the delta P and delta Q. As you can see here, delta P and delta Q, which are not more zero as in the classical case when we don't have attack, but have been evaluated by adding this minimal perturbation clipped in epsilon to be executed to modify the accuracy performance of the model. So we measure the positive and negative score when we have an adversary. Again, we clip, and we measure the sigmoid. So we have this second component here. We are measuring the loss by adding the perturbation on the model parameters P and Q with delta P and delta Q. So we have the classical loss, we have the classical loss regularized, we have the adversarial loss, and now we can build the APR loss, which is composed by Bprmf loss plus the adversarial regularized loss and the adversarial regularization. So this formula here this line of code, it is exactly the implementation of this formula. And now we can, I hope that the training has been executed. It takes a bit of time because obviously when we have this adversarial training, it takes time because it has to build attacks and then evaluate the results and retrain the model. So it is an operation that takes a bit of time and a bit of memory. Indeed, we have 8 GB running on to execute this type of approach. But yes, at the end, we can run again the evaluation and measure the model. What is the idea again? The idea is not to protect the model from shilling attacks. The idea is to study the robustness. However, take care that in the works after APR, we have seen that this model has been used not for stabilizing the training, but sometimes we have checked in our literature review that there are papers that are using the adversarial regularization as an approach, a technique to robustify the model to get more accurate recommendation. However, we should also take care that in a recommendation setting, the accuracy, it is not the only metrics that make sense to evaluate, but we have also to evaluate which are the other metrics. And if in an online evaluation, it is always the best solution for verifying if a model is working very well, we are proposing, and we have few works under review, that also other aspects should be considered, like beyond accuracy or fairness or popularity bias metrics, because it is something that we we think that should be take under consideration when a new model, a new technique is proposed, and it is an open direction to be investigated. How to protect, to make a model robust, also in this case with these adversarial perturbation model parameters, but making it robust should be not only related to the accuracy, but also to quite well performing behind accuracy approaches. And it is another research question that we leave to the attendees that are going to study this line of approaches. How much we can be safe? What does it mean be robust? How can be robust by preserving both accuracy and beyond accuracy or fairness of the model? These are open research questions that need to be addressed by the community. Okay, the training has been completed. As we can see, it is a bit makes a bit of time, and then the evaluation. Okay, in this case, we have that the training, the model has get more accuracy, as I told you before, that these techniques seems to be to improve also the accuracy of the model, and we are going to execute again the attack when we have the model adversarially trained. And if the random seed has been good for this type of experiment, okay, we have that the model defended has an iteration higher than the one not defended. And it is the reason of this approach, to have a model more robust than the one without the regularization. And this is, I think, all okay. And this is all for the first part of this hands-on session. And during the question answering session, you can ask whatever you want. I think that for now it's all, and I can give the word to Walter, that is going to present the next part of this hands-on session. Thank you, everybody.
Okay. Do you see the presentation?
Yes, we can see.
Okay.
Yes, sir.
Okay. Thank you, Felice, for this first hands-on session. And I will pose a couple of questions about that. So we have seen that we are able to create a model to perform an adversarial robustification of a model. But now the question is, can we use this kind of code, this kind of experiment for our research. And in the last years, we have discovered that these kind of experiments is not enough, because it is required that our experiments should be reproducible. And the matter of reproducibility is not an easy task to be accomplished, and we will see it in a moment. So for this reason, we decided to design a new tool, a new framework named Elliot, to realize this kind of evaluation, this kind of training with you, with the user. So this is a tool specifically designed for researchers, obviously in academia or in industry. And it has been developed by the Information System Lab at the Politecnico University of Bari, with the collaboration with Alejandro Belloin from the Universidad Autónoma de Madrid. Then you can find this tool on github.com/sysimflab/Elliot at the URL that you can find on this slide. And moreover, in the top right corner of the slides, you will find a QR code that points you to the repo. Okay. So from time to time, I will remind the attendants and the new attendants the role of this QR code. But now what I want to show you is why reproducibility is so difficult. To do that, we'll take a couple of papers that have been recently published in 2021 at TOIS by Ferrari da Crema, Boglio, Cremonesi, and Yannack, and another one that is under review by Belloin and Said. So the problem is that to make our experiments reproducible, we have a lot of potential problems, a lot of potential issues. So Belloin suggests to identify the main aspect that we should take care of to make our research reproducible. And in this sense, they say that we should take care of the dataset collection part, in which we have to understand how to download data, how to prepare data, and how to filter data. Then we have to take care about the splitting our data, because if we miss a single detail, what happens is that our experiments are no more reproducible. So we will see that splitting is not an easy task, and there are several ways to do that. And obviously, we can go beyond, and we can analyze the different problems that we can have with the recommendation model implementation. So an implementation in a specific library is completely different from another implementation, at least because of the random seeds that we use. Moreover, they suggest to pay attention on the way we filter the candidate items, because based on the different tasks, we can choose to extract, to set the set of candidate items as the unknown items for the user, or as the training set or as the test set. So it depends on the evaluation protocol. And obviously, for what regards the evaluation, several slight things can change. So the implementation of a specific metric could be different. And they've found that even though we consider the most adopted metrics, like accuracy metrics or like precision recall, they have found several different implementations. And obviously, last but not least, is the fact that we should take care of the fact that we should conduct a statistical test on the evaluation results. And we will see in a moment that all these aspects are particularly complex. And we have been particularly frustrated in re-implementing once and once again all the different algorithms to make our experiment reproducible. But also, we've said that another group of people have widely worked on that. And this is because the other group won the best paper at Rexis 2019, if I'm not wrong, showing that in several cases in recent literature, we have had in our community a lot of problems, a lot of issues in reproducing experiments and basically in presenting our experiments in the research papers. And they identify the most important issues, in this case, methodological issues that we can find in recent literature. And in particular, they mention the fact that it is very likely that we choose the wrong set of baselines to compare with. And this is a very important thing because especially with adversarial learning, we tend to compare only against other adversarial models. On the other side, we have the facility that, as you may have noted with the hands-on session done by Felice, that adversarial learning used as a robustification method as a great capability of improving the accuracy of results. But we will see that we can have other problems with that. But however, in general, we can see this kind of problem when we present our papers. And this is basically now we are talking as researchers in general. So we know that the problem is that this is what is usually required. And the fact of including other baselines is a problem because we need to implement those baselines, or we need to use other libraries to run our experiments using those baselines. Another problem is more related to the literature. So the fact that if a baseline is considered as strong, but in fact it is a really weak baseline, we tend to continue using that. So we have an effect, let's say, of the propagation of these weak baselines. And the other aspect that we want to cover is the fact that usually there is an absence at all or a partial lack of a tuning of the hyperparameters of the baselines. And again, this is due to, in our opinion, this is due to a couple of factors. The first one is that it takes a lot of time, obviously. And the second one is that we need to implement an hyperparameter optimization strategy. So for all these reasons, we decided to write a tool for us and for our community to start making reproducible experiments. So it is like a facility for the community. So they suggest to follow some very important guidelines. Some of them are derived by the NeurIPS guidelines, like publishing the source code for all the models and thus including the baselines. We should provide the data sets, and we should ease the reproducibility of our experiments. But also they suggest to put in our paper a lot of different information that are needed, that are the minimum information needed to reproduce our experiments. So all the assumptions that we use, we should be really clear about the pre-processing steps, and we should report the hyperparameter optimization details. So without going beyond these, even here, the problem is that very likely we have a lack of space on our papers. So even though we want to share with the reviewers our experiments, it is a mess, it is a problem, and we do not know how to do that in an easy way. So the funny fact is that these two works are from 2021. So when we started working at Elliott in late 2020, around October, we had no knowledge that these two groups were working on those papers. But this is a signal that as a community, we have this kind of need. So as you will see in a while, we have tried to create this framework that makes our lives much easier in running and reproducing experiments. And here we will see that we will focus on the framework to go through two main examples, one with adversarial learning and the other with generative adversarial networks. So, but the real question is, how does it work? Okay, the underlying idea is that what we want to conduct is a whole experiment. So we had to define the full pipeline that we need to realize, to conduct the experiment. So at the very beginning, what we need is to load data. So Elliott should load our data, our data set or whatever, and should be able also, and we have seen it with GANs and with adversarial learning, it should also be able to load and handle side information. Then we'll see that there are a lot of different pre-filtering algorithms that are used in the literature. So at the beginning, we don't know which kind of pre-filtering strategy we want to use. So what we did is to try to implement as much as these strategies as possible to preserve the freedom of the researchers to do their research, basically. And then the other problem, the other big challenge is to face the splitting problem. Because honestly, we have a lot of different possible splitting that you can find. And in the literature or in the handbook or whatever, you can find that even though you change a slight detail of the splitting procedure, everything changes. So your results are no more comparable. So maybe a reviewer could say, okay, your results are not reliable and you cannot publish, or you can have problems in the future. So even here, the goal was to implement as much as splitting strategies as possible to make it easier for the researcher. And then we focused on the recommendation models. And we implemented the 50, to date, 50 recommendation models that you can use. And if we go back for a moment, we see that one of the suggestions that come from Dacrema, Cremonesi, and Yannack is the fact that you should compare your method against the recommendation models that come from other recommendation families. So even a lot of recommendation models that have been already implemented coming from several different recommendation families is a plus, because we can write and we can define our model, and then we have all these different recommenders that we can use for comparison. And obviously, a big lack that we have in the existing recommendation framework is that the number of evaluation metrics is very, very limited. And as Felice and Tommaso and Yashar were mentioning before, the problem is that today we need to evaluate, and that is correct, we need to evaluate a lot of different dimensions. Is no more enough to evaluate only accuracy or errors. Now we need to evaluate the bias. Now we need to evaluate fairness. And obviously we need to evaluate novelty, diversity, and so on. So we needed to create for ourselves, and then for all the community, a framework to avoid re-implementing all these metrics. Because here the problem is that, okay, I can use a certain library for some methods, another library or a GitHub clone for other methods, and then another one, and then another one. And in the end, we can use another library for the evaluation of the recommendation results. But in the end, it will be just a mess of scripting files. So we tried to build a unique pipeline to do everything together. And in this way, we don't have problems with the possible and different implementations of the metrics or the recommendation methods and so on. But also in those situations, we should have a very big problem. That will be the statistical tests. Because if we obtain from an external library the recommendation results, let's say on a system basis, it will be impossible for us to compute statistical tests. Or better, we can use some let's say exotic solution, like the partitioning of the user, then the recommendation, and then we could compute these statistical hypothesis tests. But here we have put all together in a single framework to let us compute it in a simpler way. And obviously, now we can focus on the outcomes. And what are the outcomes? Are those files that we require to put the important information on the paper and to analyze the results. So we have the evaluation results, but also we have the infra-model statistics. So if we are exploring the hyperparameters, I want to know what is happening when I change a parameter. So we will save all this information, but also we can save the model weights, so that at a certain point we can decide to rerun or to continue the learning. And what more, obviously we save the best hyperparameters for each model and the statistical tests, and in the end we also save the recommendation files that could be useful to implement further metrics. And all of these happened at the same time that the other groups were working on the same topic. So now another problem comes. How can we say to this framework, to this tool, that we want to perform a specific experiment? That's a problem, right? And because trying to pass all this information through a command line, it could be insane. Okay, so we decided to adopt another strategy, that is to create a very simple and clear configuration file, so that in the end, you can write your configuration file and run it. Okay, so this configuration file will contain all the important information that makes your experiment reproducible. And this is important because we have seen that when the other groups were working, they suggested that, okay, you have to provide all this important information, but we do not have a scheme of this information. We are trying in our community to create this scheme. But what is better than a single configuration file that recreate exactly the same results? So we defined, using YAML, this kind of configuration file in which we state all these different aspects of the experiment, from the data loading to the recommendation models and the evaluation part. So what we are doing right now is to provide you all these details before going through the configuration files that we used for adversarial learning and generative adversarial networks in such a way that you can play with these values. You can run these configuration files as they are, or you can start modifying them, and you can prepare your own experiments. So we will we'll go through a quick overview of these capabilities of the framework, just to give you the tunes to play with these values. So if we focus on the data loading, what we can see is that we provided 3 different kinds of data loading strategies. The first one is that you want to read the old data set. Okay, and you can find in the top right hand side how you can do it. Okay, in this case, you say that your strategy is dataset, and you can pass a dataset path. Another option, obviously, is to have your dataset already split. So in that case, what you can do is, okay, you can say the framework that your data is fixed, and you can pass the SQL files. But moreover, what you can do is to perform, and we will see it, a complex splitting procedure, and with Elliot, and then you can save it on your hard drive. And the next time you can use the splitting that you have been already conducted. And that is the case of hierarchy. So for what regards the pre-filtering operation, we have a lot. We have said that we have a lot of possibilities in our community. So we have the most adopted strategy, that is the threshold based. And in this case, you can define a fixed threshold. Like, let's say in Mobilence, you can say that you use a fixed threshold of 3, and you get all the transactions with values that are 3 or greater. But also you can make Elliott compute this threshold as the average of the overall data set. And also you can ask Elliott in the third example on the right to compute the average on a user basis, and then he used this personalized threshold to filter out the non-relevant transactions. What more? We have a lot of other pre-filtering strategies, such as the key core, and among the key core we have the user key core. So we want to keep only the users that have a certain number of transactions, and we can do it in Elliott, and you can see it in the right hand side. But also we can use item key core in the same way, or iterative key core, because we want to set a key core of 5, but we want that both users and items should respect this key core. Or maybe, since the iterative key core could take a lot of time, we can decide a certain number of rounds of key core that we want to apply. Or maybe what we want to do is the opposite. So we want to keep only the users that are below a certain number of transactions. So we want to keep only the cold users, and we can do it, obviously. Now we can move to the splitting strategies. And here you will see that in the recommendation task, we have a lot of different splitting strategies that we can use. The most realistic one, and the one that it is mostly used in the recent works, it is time aware. What does it mean? It means that we use the temporal signal to define what is in the past of the recommendation model, and so in the training set and the validation set, and what is in the future of the recommendation model. So here we defined 3 main strategies to do that. One is that we can pass the timestamp as it is, or maybe we can compute the best timestamp based on an analysis of the users. So we want to maximize the number of users, so the core of the recommendation system, preserving a certain number of transactions in the training set and in the test set. Or the most adopted is the temporal doubt and temporal leaving out, in which we retain, let's say, the latest 20% or whatever of the transactions for the test set or the validation set, and we keep the remaining ones for the training set. And obviously we can do the same with leaving out, and we can define, let's say, 1 or a certain number, and we want to keep for the test set or the validation set. But also another very adopted strategy is the keyfold cross-validation, and we implemented it, and we can use it in its common fashion, so keyfold cross-validation. But also you can define, and here is particularly easy because you have you don't have to implement anything. You can have a nested cross-validation in which you realize key-fold cross-validation for splitting with the test set, and then you have another cross-validation for splitting the training set and validation set. But also with larger scale data sets, we can see that we have another kind of splitting that is based on the random subsampling. So the basic case of subsampling is the classic 80-20 holdout, but we can perform a certain number of holdouts. Okay, so without the partitioning that is needed for key-fold cross-validation, but following the same strategy of 80-20 holdout or whatever. So here we have the possibility of using holdout, leave n out, so leave one out or whatever, but also to realize a key repeated version of this splitting. And this is particularly helpful when we have a very large data set and we want to let's say, to realize 10 folds, but in each of these folds, we want to keep for the test set, let's say, only the 2%, because the 2% is 1,000 transactions. Okay. Now we can go through the recommendation models. So we will see the different recommendation families, and we obviously start with the adversarial learning. And here in Elliott, we have already implemented two different models that are adversarial matrix factorization that you can run as it is, and adversarial multimedia recommender that needs visual features to be run. Again, for the new attendance, you can see that in the top right corner of the slide, you can find a QR code that points you to the GitHub repo. So if you are interested in collaborating with us, or your proposal or whatever, do not hesitate to contact us. And if you find any issue, please tell us and we will work on that. And obviously, if you like it, give a star. But also we have a lot of other families, and we will try to go a bit faster on these families. For instance, we have very old recommenders that are used in the basic frameworks like MyMediaLite, and we have tried to reproduce. We have reproduced their logic in such a way that we can use them against the modern models. But also we have very high quality models like variational autocoders, and in general autocoders like collaborative denoising autocoder that have been found as some of the most prominent recommendation model of the recent years. But also we can use content, and in this case, obviously, we have implemented the giant of content-based recommendation model that is vector space model, and we will see it in some minutes. The fact that we have implemented IRGAN and CFGAN, that are two models I have explained to you before in the previous part of this presentation. Moreover, we have a couple of graph-based recommendation model, and that this could be interesting to see what happens between adversarial models and these kind of models, or generative adversarial network and these kind of models. But also we have some models, and in this case, a model that comes from ISWC that make use of more structured knowledge. In this case, are knowledge graphs. So in this case, what happens is that the recommendation model uses a different kind of side information, and it is able to process it. Then we can start with some recommendation families that are, let's say, a bit crowded, like latent factor models. As Felice was mentioning, latent factor models are very widely adopted. And this is due to the fact that they show impressive performance with variational autoencoders and those kind of models. And here we have a lot of different implementations of several latent factor models. And you can try them and you can use them to compare your model with. And also we have another crowded recommendation family that is artificial neural networks, because in recent years we have seen the emergence of several recommendation models that are based on ANN. And if you are into the field, you can see that you know the majority of these models. But also we have implemented some very important collaborative filtering algorithms like item KNN, user KNN, attribute item KNN. So here we can use also the content and attribute user KNN. And here we have to mention that we have connected with SciPy and scikit-learn to provide more similarities. So here you can use item KNN, user KNN, and so on with 27 different similarities. So you can try them as you want. And obviously in your analysis, in your experiment, the two unpersonalized recommenders like such as most popular and random have to be present. So we implemented them and you can put them in your experiment. But also, and Felice started mentioning them, in recent years, we have the emergence of visual recommendation models. And we have a lot of visual models that you can use and you can try. But for what regards the evaluation, we have said that we have a problem in general with the fact that if someone is proposing a model, recommendation model, you cannot find the implementation of the metrics. So you have to rely on external libraries or whatever. And here we can see that we implemented a lot of different evaluation metrics. In particular, we implemented something like 36 evaluation metrics. And obviously the first family is accuracy for ranking-based evaluation. And we will use this family to explain how you can write in your configuration file the evaluation part. Obviously, what we first need is to define the number of recommendation that you want your recommendation model to provide, and you can write it for your using your top key field. You can see it in the right-hand side. Then we start defining our evaluation, and you can see that we define more than one cutoff. And this means that we are asking our evaluation module to evaluate our recommendations with a cutoff of 10 and with a cutoff of 5. So thus producing different outcomes that we can use in our paper. And also we can see that we have a field that is called simple metrics. What does it mean? It means that the majority of the evaluation metrics do not require additional information. So we can just point the name and the module knows what has to be done. So in those cases, we can just put the name there, and we will compute all those metrics. In this case, we have only used 3 accuracy metrics. that are NDCG, precision and recall. But also, we know that to evaluate our models, what we need is to define a threshold, a relevance threshold, because when we analyze our test items, we have to decide if a test item is relevant or not, and we use that. Moreover, we will see that, and here we can see it, that we can provide statistical significance hypothesis tests. And here what we're doing is using students pair t-test and Wilcoxon test. But also there are some metrics that requires some more information. For instance, we have the Sorensen dice coefficient. That is the metric that you can find in DSC. So these kind of metrics are considered as complex metrics, and we pass additional information in the way you can see on the right-hand side. But also we can use some other side information that could be, let's say, a category of items or groups or user groups or whatever. And this is the case of sRecall that we have put here just to explain what we are doing. For what regards the accuracy of recommendation, we can see that you can find the area under the curve, the group area under the curve, and so on. So please remind that area under the curve in its original implementation is not user-based. So if you want to use the user-based implementation, you have to use the second one, so GAUC, and so on. But we have a lot of different metrics, and also we have rating metrics, but also coverage metrics like item coverage, user coverage, and so on, novelty metrics, diversity metrics, where we can measure also the distribution inequality of the recommendations, and more modern evaluation metrics such as bias and fairness metrics. What we can do now is also to let the user prepare the hyper-optimization strategy. And in this respect, what Elliot provides is the grid search, Bayesian optimization with trio Parson estimators, so TPE, and adaptive TPE, random search, and mixed search, and simulated annealing using the HyperOpt library. And also we can define the search space, because the search space is very important to find the best parameters in several ways that are defined by the HyperOpt library. And we have already seen how we can pass the statistical significance of the results. So we can now we know all the important points, so the bullet points that we can use to tune, to modify, to play with our configuration file that you can find both in the GitHub of the hands-on session and in the GitHub of Elliot. And you can connect to it using the QR code in the right-hand side top corner of the slide. So now we can focus on a specific adversarial model, and I could give the stage to Felice to explain this model and the model configuration. Then I can continue.
Okay, thank you, Walter. Okay, basically, as you can see in these bullet points of the models, in this case, what we have done is to execute an adversarial matrix factorization model, which is a Bprmf using APR. we have selected as splitting strategies a random alt-out with the 80-20 for training and test. We select an evaluation metric has its ratio at 15. We applied also the t-test with the students per t-test and Wilson. We trained for 10 epochs. We selected these patch sites, and we have also the bias regularization, but also the adversarial regularization coefficient. So in the next slide, I think that Walter, if you can move to the next one.
Yeah.
We have the configuration file that I have shared you the link in the chat, where we have the experimental section, where we have the data set, the splitting strategies, the evaluation metrics, and in this case, we tested iteration, DCG, EFD, ACLT, and APLT, so different type of metrics. And then we have our model. We can see that we have used a TPE strategies with hypermax evaluation epochs equal to 5. We trained for 10 epochs, and we have created a search space using the Q uniform and log uniform strategies for the number of factors and the learning rate. And in the second file that you can see here on the right, we have the running file where it automatically downloads MovieLens 1M. It creates the strategy, the split, it saves it directly in the directory that is used during the experiment. So simply running the second file with the Python sample adversarial .py command, you can have the execution of the full experiment, and at the same time it is fully reproducible. In this case, it can be executed on the GPU one, but if you are going to use a machine without GPU, it will automatically run the experiment on the CPU. So I think in the next slide we can have the results for this execution.
Okay. I want to mention that here in this file we avoided to show the recommendation model we are comparing with. That is the neural matrix factorization model. So here what we want to see is that we want to cover all the possible outcomes that we can have. So the first one is the list of the best hyperparameters that we obtain. So here you can see that we have like a recap of what we are doing. So what is the validation metric, what is the cutoff that we are considering, and the threshold. And here also we can see the characteristics of the winning model among the all the possible alternatives that Elliot has computed. And so we can see that we have some specific values for the learning rate and regularization part and the adversarial part. But also we can see that we can compare AMF against the neural matrix factorization, and we obtain directly the tables with the table separated values for all the different metrics. So HR, NDCG, EFD, ACLT, and APLT. But also we can see that in the table below, we have the different values that we obtain for each metric for each considered combination of hyperparameters. That is what I was mentioning before. So we can analyze in depth our models. And as Felice was mentioning, we have decided to compute the statistical significance test. And in this case, we computed the students per t-test. And here you can find another file that provides you all the details that you can use. And we can see here that all the results are statistically significant with a p-value of 0.05 for sure, let's say. And also we can analyze the Wilcoxon test, and we obtain the results, and we can use them on our papers, and the situation is basically the same. So then we can move to the generative adversarial network example, and again I give the stage to Felice.
Thank you, Walter. Okay, in this case, we are supposing that we are going to prepare an experiment to compare GAN-based approaches. For now, we have implemented IR GAN and CF GAN, but basically we can implement whatever GAN-based model we want. And we are going to, also in this case, to apply search strategies across the parameters. In this case, the metrics are hit ratio, RMSA, item coverage, and the popularity RIO and the popularity RSP, which are two popularity-based metrics proposed last year at CIR. And if we go on the next slide, we have the configuration file. And as you can see here, for the IR gun, we are using a grid search because without the specification, it is a grid search with a validation rate equal to 5. We are exploring a search space by specifying two types of factors, 50, 100, two types of learning rate. We are using as the prediction model, the generator, because we can use also the discriminator. And then for each epoch, we have two training inputs for the generator and one for the discriminator. At the same time, since we don't know if the pre-training strategies of both generator and discriminator are something useful, we have also selected the possibility to pre-train or not pre-train the generator and the discriminator for two epochs. And then the sample lambda is a parameter between 0 and 1 that is used during the sampling generation, that is a specification of IR GAN. At the same time, we have applied an analysis of CF GAN, and again here we have explored two number of factors. We have selected a learning rate in a double space. Also, we have used the regularization coefficient for the weights. We have specified the number of epochs of training the generator and the discriminator. And then the last two parameters are model-specific parameters, where major details are defined in the original paper, which are basically two different implementation of CF GAN. And L GAN is the regularization factor of the GAN approaches. So if we move to the next slide, so we can, with a simple command, we can run the full the full experiment, and at the end, in this best hyperparameter file, we can have the information of the best model for both the model that we have trained. So for instance, for our GAN, in the setting that we have explored for the search space, not training the generator but pre-training the discriminator with two epochs is the best solution, is the one that got the best solution. While using one epoch for the generator and one for the discriminator seems to be the best solution for the CF GAN. It is interesting here to analyze that basically these type of studies are very time consuming because we have to implement everything. While with this framework, we can basically study in depth what does it mean to have trained, for instance, the generator and the epoch and the discriminator for different type of epochs, in order also to study if the pre-training strategies or not are useful for having best accurate or not model, but also at the same time has a validation metric or evaluation metric we can use also behind accuracy metrics if we want to tune a model with respect another objective that we want to address for. So as you can see in this file, we can have the best configuration of parameters that can be useful to think more on our experiment and other insights for the community. In the next page, I think we have also the results.
Yeah. I will add a couple of things to what Felice has mentioned so far. That is the fact that obviously you have these two configuration files that are basically two very small experiments, so small dummy experiments that we created in such a way that you can run it in a limited amount of time. And here you can see what happens. Obviously, our GANs have not converged yet. In a couple of epochs, it is almost impossible. So we can see that we have the RMSE that is going to infinite. But in general, the very important point that has tackled Felice is that it is everything there. So you can use it, you can change, you can try, you can play with it, and you can find what happens. So here you can see the performance between comparing IR GAN against CF GAN, and also, as before, we can see what happens within the CF GAN model. But if we remind what we decided to do with IRGAN, we discover that we performed a quite large exploration of the search space, and this is just let's say an half of the old table that we can obtain. Obviously, in this case, we use just a limited number of epochs, but in general, this is showing to you that we can explore much more the search space with this kind of tool. And so I think that these are the main things that we wanted to show to you. So how to create the model from scratch with the mathematical details, and on the other side, how you can use a prepared tool for you to realize your experiments in such a way that you can create experiments that could be reproducible and could be used in your research. So, Felice, I think
So I
that
think it's time
yeah.
for question answering. So if
Yeah.
someone has some question, we are really here to answer and also happy to answer.
Yeah,